Say you've got a containerized API and a background worker, and you don't want to babysit a Kubernetes cluster. Azure Container Apps is the serverless container platform that sits between app service and full AKS. In the next few minutes, we'll dissect one realistic reference architecture: an external API behind managed ingress, a private worker driven by a queue, secrets in Key Vault, and event-based auto-scaling. We'll trace how a request flows, why each piece exists, where it fails, and the trade-offs an architect actually weighed. This is not a getting started tour, it's an anatomy lesson. Here's the wiring. A client hits Azure front door, which terminates TLS and routes to the Container Apps environments built in Ingress. Inside that environment live two container apps: an API app with external ingress, and a worker app with no public endpoint at all. The API writes jobs to an Azure Service Bus queue. The worker pulls from it. Both apps pull images from Azure Container Registry and read secrets and connection strings from Azure Key Vault using a managed identity. The Container Apps environment is the key boundary here. It's the unit that shares a virtual network and a log analytics workspace, and every app inside it can reach the others by name. Walk a single request through. The client calls a custom domain on front door, which gives you a global edge, web application firewall, and caching. Front door forwards to the environment's ingress endpoint, which is an Envoy proxy that Container Apps manages for you. Envoy load balances across the running replicas of the API app and can do traffic splitting between revisions. So a blue-green or canary rollout is just a wait on two revisions. The API validates the request, drops a message on service bus, and returns 202 accepted. The synchronous path ends there. The worker picks up the message asynchronously and does the heavy lifting, so a slow job never blocks the caller. Auto-scaling is where Container Apps earns its keep. Under the hood, it runs KEDA, the Kubernetes event-driven autoscaler. The API app scales on concurrent HTTP requests, say 10 per replica. The worker doesn't scale on CPU at all. It scales on service bus queue depth, adding replicas as the backlog grows and removing them as it rains. Both can scale to 0 when idle, which means you pay nothing for the worker between jobs. But scale to 0 has a real cost: a cold start. The first request after idle waits for a replica to spin up, often a second or several. If that's unacceptable, set minimum replicas to 1 and accept the always-on bill. That's the central trade-off on this diagram. Every box on this diagram can fail, so design for it. If the worker crashes mid-job, Service Bus redelivers the message after the lock expires, so make your handler idempotent or you'll process twice. Poison messages should land in a dead letter queue, not loop forever. If Key Vault is briefly unreachable, the platform caches secrets at revision start but won't see rotations until the next revision, so plan rotation as a deployment. Container Apps revisions are immutable. A bad image means you shift traffic back to the previous revision rather than patching in place. And remember, an environment is a blast radius. Everything in it shares the network and the log analytics workspace. So isolate truly independent workloads into separate environments. So why pick Container Apps for this design at all? Against full AKS, you give up direct control of the Kubernetes API, custom operators, and node-level tuning. In exchange, you delete an enormous amount of operational work. No node pools, no cluster upgrades, no Envoy to run yourself. Against app service, you gain real container orchestration, multiple apps per environment, Dapper integration, and event-driven scale to 0 that app service can't match. The rule of thumb: reach for Container Apps when you want containers and auto-scaling without owning a cluster, and only graduate to AKS when you genuinely need its control surface. Pricing is consumption-based per vCPU second and gigabyte second, so check the current Azure docs before you model cost. Here's the deployment in its simplest honest form using the Azure CLI. You create the environment once, then create the app pointing at your registry image, set the target port for ingress, and define the scale bounds. In a real pipeline, you template this in Bicep. Wire the managed identity to Key Vault and the registry, and define the KEDA queue scaler in the app configuration. But this is the core shape: environment, then app, then ingress and scale rules. Notice min replicas 0 and max 10 right there on the command. To recap the anatomy: front door at the edge, a container apps environment as the boundary, an external API and a private worker decoupled by service bus, secrets in Key Vault behind a managed identity, and KEDA driving event-based autoscaling. The architect's central trade-off was scale to zero savings versus cold start latency, plus choosing managed simplicity over AKS control. Your one concrete takeaway: decide the cold start question first. If your PI is latency sensitive and user-facing, set minimum replicas to 1. If it's bursty or a background worker, let it scale to 0 and bank the savings. Everything else on this diagram follows from that one decision. And always confirm current limits and pricing in the Azure docs before committing. If this helped, do me a favor, hit the like button, subscribe, and tap the bell so you don't miss the next one. See you in the next video.